All right, I believe uh, it's my presentation now, and I'm going to be talking about persistent data structures in Raku, which is a grant that I am work that I'm currently doing pursuant to a grant. Let me see if I can get the chat window here. Can someone confirm that you can hear me? All right, that is great. All right, so for those of you who don't know me and didn't meet me at my talk yesterday, my name is Daniel Sockwell, although you might know me better as Code Sections, the username I use online a lot. And as I said, this presentation is on persistent data structures, which I'm implementing for Raku. This is going to be a pretty quick talk, just 20 minutes, and I do want to leave a little bit of time for questions. So I'm not going to have a whole lot to say, but basically what I want to tell you is why I'm trying to add persistent data structures, how that will be implemented, and then little bit of time for bike shedding about the name of these different data structures, because I could use y'all's help. So as I said, this is a work that I'm doing pursuant to a grant proposal that I wrote and that was funded. I haven't done a tremendous amount of implementation work because there have been some logistical difficulties in getting a grant on the grant committee's end in terms of getting a grant supervisor and just the logistics of that. But I have started the implementation work, done about 20 hours so far, and I'm looking forward to doing a bit more as the month goes on. The first thing I want to talk to you about is this why question, though. Why did I propose this grant? Why was it funded? Why does it make sense to have persistent data structures in Raku? Well, basically, all of this comes back to immutability. As many of you, I'm sure, know, the immutability is extremely popular and extremely helpful in writing robust code, especially if you're writing in a more sort of functional programming style. Immutable data is much better for multi-threaded code because another thread can't change the data out from under you. Immutable data is just much easier to reason about because you know that the data you have is the data you put into that container or that variable. It's nothing else has changed it, especially as you sort of scale up and get to bigger and bigger programs. Having immutable data is extremely helpful. However, in many programming languages, having immutable data also comes with a pretty high cost because the main way, well, I mean, by definition, when you have immutable data, that means you're not changing your data. And that means that if you have an array of 1,000 elements and you want it to be an array of 1,001 elements, in a mutable world, you just mutate the array and add an additional element. In an immutable world, you need to allocate an entirely new array, copy each of the 1,000 elements into that new array, and then copy a 1,001st element into the array. That gives you a new copy that allows you to do the sorts of things that you might otherwise do through mutation, but while preserving all the benefits of immutability. That is great for sort of programmer ergonomics, but it is not very good for performance. It requires all of these copies. So the big idea with my grant and with shared persistent data structures is to say, how can we get the benefits of immutable data structures without the cost of copying all the time? And the basic idea, I want to show you this diagram here. The basic idea is that it is to convert your data structure into one that is somewhat tree-like, and it's tree-like both in the TREE tree sense and tree in the TRIE, sometimes pronounced try, like it has similarities to both of those data structures, but the basic idea is, as this diagram is illustrating, when you're adding this new C node, this new element to your array that contains the value C, all of the blue nodes and the pink or purple nodes here are actually added, but everything else is shared. So the idea in a sort of big picture sense is that you keep all of your shared data. You share as much of the old data as you can, anything that is totally unchanged, and then you add in sort of path copying to point to the specific data that you need to add, just to sort of track the changes. So how does that work under the hood? So under the hood, this is an illustration that I'm going to walk through of how this works internally. But what I need to tell you before walking through this diagram is, here each of these nodes is shown with two children, which is to say this diagram illustrates persistent data structure with a branching factor of 2. That's just to make it fit on the diagram. In practice, the branching factor is usually much higher than that. It could be up to 64 for a 64-bit architecture. There's some sort of theoretical reason that 64 would be the best. In practice, 32 tends to be the ideal branching factor for reasons that have to do with cache coherency, and you actually end up filling up your cache lines and having some cache misses with when you go all the way up to a 64-bit branching factor that you can avoid with a 32 branching factor of 32. But that's something that I can play with and test out for Raku and profile as I develop this data structure specific for Raku. But so with all that said, imagine that in practice, this would be a lot more than 2 nodes, but the basic idea is you start with a head node that tracks how many items are in your vector, and then at each level, you either get to the leaf node, or you branch out to another internal node, and then you get to a leaf node that has just the branching factor number of elements. So here 2, in practice more like 32. And what that means is you can always access a particular element just by following a single chain down to that node. And to go back to our path copying example, if you want to append an element, you only need to change the path that takes you to that element. So the pink nodes here are the 2 that you need to add. The blue nodes are the 3 that you need to change. The orange are the nodes that remain. And as you can see, by following the arrows, the new blue nodes end up pointing to a lot of the existing orange nodes. So much of the tree structure is not at all, there's no need to copy the vast majority of it. Let me just check the chat to see if there are any questions. Yeah, this is somewhat similar to a try with frequencies, but those are related data structures, although they would have different use cases. As I mentioned before, this is something that is a well-known data structure, and it's one that has been discussed in academic literature for the past 20 years. It's actually was implemented in Clojure a number of years ago as one of the sort of first features of Clojure for its 1.0 release. And so there is a lot of prior art that I'm sort of following along with. So that's part of the reason I think this was a good fit as a grant proposal is that it is sort of a well-trodden path, but it will get a feature that will help Raku be on sort of an even ground with other languages that support functional programming as well as Raku. Okay, so the last thing I wanted to talk about before turning this over to questions was bike shedding on the name, as I mentioned, because that's one area that I would like some help with. My initial idea, as I let out that, excuse me, my initial idea, as stated in the grant proposal, was to call all of these hat. So you'd have list hat, map hat, set hat, bag hat, mix hat, etc. And the idea there was that the underlying data structure that backs each of these is frequently known as the hash array mapped trie. And to make that pronounceable, I was going to drop the M, which is not really essential to the name, and think of them as hash array tries. But I didn't love that idea, and I love that name. And then Jonathan also pointed out that that sort of leaks implementation details. You know, it really isn't essential to these data structures that they're implemented with a hash array map trie. That is by far the most common implementation strategy, but it isn't at all essential. And, you know, encoding that into the name feels a little bit icky. So I went back to the actual idea. What is this if it's not a hash array map trie? Well, really all it is a persistent, shared, and immutable data structure. So I started to think, how can I put together persistent, immutable, and shared in some combination, and just sort of went through a process of elimination to figure out what names would work. I don't really like PIS as a name. That invokes a different process of elimination. I don't really like PSI as a name because that sounds like pounds per square inch. I don't really like IPS. That sounds like the plural of IP addresses, especially in a programming context. ISP sounds like internet service provider. Spy sounds like something about like observing your code or spying or something. So yeah, that let me, as someone has already guessed in the chat, led me to SIP. So that would get us, instead of list hat, I think it would be SIP list, SIP map, SIP set, or maybe set SIP. I'm not sure about the order there, but so that's my current thinking. But I'm open to ideas either in something along these lines or in a different vein altogether. So yeah, as they say, naming things is one of the two hard problems. VoIP protocol. I haven't heard SIP as a VoIP protocol, so that is one reason to think one strike against that as well. So like I said, naming things is a hard problem. Definitely open to ideas there, and I would be happy to take questions as well. I see in the chat someone saying that there are 3 hard problems because it's off by 1 errors, but that can't be. The joke is that there are 2 hard problems in computer science: cache invalidation, naming things, and off by 1 errors. It doesn't work if you say that there are 3 hard problems, and there's no off by 1 error. Let's see, Dan, it looks like you have your hand up.
I don't have any great ideas for names, but I guess I'm just thinking given that this, this is based on prior art, Clojure sort of famously has immutable data structures. I've actually used Clojure a bunch, but that was a while ago, and I'm now blanking on what they call them. So, I mean, have you done a survey of the languages that do offer data structures, either built in or as modules, packages, whatever they call them? Is there some sort of consistent name that we can just steal, or is it really all over the board?
It's fairly all over the board, especially languages like Clojure that have them. Like Clojure has these data structures as their base data structures. So they have a list and a vector and a map data structure that, we already have names in. We're already occupying those names. So they don't have them denoted separately, since their built-in data structures are all immutable. And then they have, I believe they have a way to either directly or calling out to Java, I forget. They do have a way to have some specially mutable data structures, but they have sort of an inverted naming convention because they are immutable by default. And there are some languages that have these as libraries. They do tend, I think JavaScript has it as a library, but because JavaScript doesn't have a separate notion of list, they just have arrays. I think they use list to be, much like we do, to be the mutable version. And that would be one option, the sort of name floating around in the list space that we have not already assigned a meaning to is vector. I don't love that, partly because I have spent some time with Rust where vector is the immutable version and array is the mutable version. So something in my brain rebels at the idea of making vector the immutable version, but that would be one option if we wanted to go pick a new name for things. But I'm seeing some chat, no, not vector, which is again kind of my instinct as well. But a broader survey, to your point earlier, Dan, could be a good option. Like I said, I've made a note of a few, but certainly not a comprehensive survey. And let's see, William, you have a question as well?
Yeah, please call me Bill, Daniel.
Bill.
Yeah, you're just going to have to back up a second, explain to me your persistent data structure versus red-black trees, because I always seem to forget this point.
Sure. So a red-black tree is a similar idea in that it's a self-balancing data structure. It's been a while since I've implemented a red-black tree, but that works along similar lines, but the hash array mapped trie backed persistent data structure, it is going to have many more buckets per node, and is going to it is going to either hash or use the index value to traverse the tree, and doesn't have any sense of coloring the nodes the way a red black tree does, and thus doesn't need to rebalance in the same way that a red black tree does. I'm not sure that was a fully comprehensible explanation, Bill, but I'd be happy to send you a link that compares the two.
Yeah, and that's just sort of that's an entree to the question of whether or not you can kind of riff on that design, to use a name. Obviously, RB is not a good acronym, but maybe BR. We get the Brazilian connection going here.
I
anyway,
don't think so, because they are similar enough, but distinct in use cases. my first instinct is that it would confuse people to pull in the idea of red black trees, because these are trees, but are not red black trees under the hood. So I think that would risk increasing confusion.
Yeah, and yeah, sorry, go ahead.
No, I like the way you're thinking. That's a helpful approach to sort of come at it sideways, and I like that. All right, well, I am about at the end of my time, and I don't see any other questions, so I'm going to stop my video at this point and turn it back over to Andrew.